So very quick comment on the BJTs. So for example, there's nothing connected to the BJT, but just self. I mean, there's no emitter resistor or collector resistor. Then if I say whenever VBE, for example, is 0.71 volt, and I got an IC, which is 1 milliamp, okay? Do you really need a resistor here to have this statement? So the VBE is applied to here, right? And IC is flowing into the collector. So it doesn't matter if you have the resistor or not, because this combination is actually going to give you, will allow you to calculate for what? We have never calculated because it's not necessary. Remember that equation? So if I say when VBE is 0.71 volt, IC is this, okay? Then I'm gonna ask when VBE is 0.69 volts, what is IC? Can I do that calculation? Yes, you can, right? So just use this equation. It's IC1, which is that, over IC2 equals to IS over IS. It's the same temperature, so IS is not changing. EVBE1 T over EVBE2 over VT. So the VT is a constant, but VBE is changing. And so VBE is given, VBE1 is given, so this is given, and this is also given. And this is also given here, right? That's VBE2. You can definitely calculate IC2, right? Okay. That's a trick there. Just let you know that. So there are some remaining stuff for C5 layers, for the poly layers. The reason I want to do that is I want you guys to know how to design capacitors in a silicon wafer, in a silicon chip. So resistors make sense. What are the two materials we have learned for resistors? Remember? NWELS or the poly, okay? And now what about capacitors? So capacitors are two metal plates with dielectric material in the middle, right? How can I make caps? Can you just have, so here's a P sub, and the first one will be FOX, right? The fused oxide. And then keep going, what's the next? The polys, right? So how can I make up two plates? Can you have one here, and then just do this? Hey, that's a cap. What's the problem? I mean, you got one plate here, and make a via, and that's a cap. Why is it bad? It's bad idea. Why? How can I modify the cap? You can change the distance, right? You can make them further away from each other. But how can I change the area? Make it longer? But because the thickness here is very limited, so you cannot change the area really much. So that's why in the C5 technology, there are actually two poly layers. So on the left-hand side in the toolbox, right, you have multiple components in there. There are actually two poly layers. Poly 1 are being used as gates. So poly 2 is just another poly layer. It's actually uses FOX. On the top of FOX, there's another layer. It has two different poly layers. at a different height. So they're not changing the distance between the, or the thickness of the dielectric material in between, because you cannot change it. So that's P1, that's poly 1, that's poly 2. They're in the same insulator layer. You know, but I can make a cap in this way. You get a metal, because on the top of the poly is a metal 1. I get another via, that's metal 2. The metal 1 as well, right? So I got 2 metal contacts, and it's going to form a cap. So the effective area for the cap, remember the cap, C equals to what? Epsilon times A over L, or A over D. Let's use D. It's the distance between the two plates, right? So for this cap, what's the effective A here? Only the overlapping area here, right? The reason has to be you have to extend this bottom plate because you need a via to make the contact to the bottom plate. But effective area is only here. We are calculating the capacitance of it. Okay, and there are several parameters you need to know. So Cox prime, you will see this a lot. It's not Cox. So the capacitance of the oxide, right? It's Cox, COX. Cox prime equals to epsilon R times epsilon 0 over Tox. So Tox is the thickness here. So the thickness of the oxide in between the two plates. So which equals to epsilon ox over Tox. So what is epsilon ox and what is epsilon R and epsilon 0? So epsilon, I think it's epsilon O, sorry. Epsilon O equals to 8.85 times 10 to the negative 18th A femto per micrometer. So what is AF? What is A? So A means atoll, which is 10 to the this is 10 to the negative 18th femto the farad per micrometer, which is also 8.85 time. You don't have times then anymore because A atoll is 10 to the negative 18th. That makes sense. So ATTO, which is 10 to the negative 18th. So what's there are another units. Zapto is even smaller, which is 10 to the negative 21st. And Yocto, I've never used these ones. I just want to give you guys more examples so you are aware of these kind of different units. That's 10 to the negative 24th. Okay, if you see AF in the textbook, so you'll know it's 10 to the negative 18th. So what's the larger one compared to A? Femto, right? So what's femto? So what's the next? 1,000 times larger than this one. What is that? Pico, right? Next. Nano. Oh, negative 9s, right? So nano becomes huge in between those units. Not small anymore. It's huge. Epsilon O is the it's called the permittivity of the vacuum. permittivity epsilon r is the permittivity of an insulator. So Cox prime is this because we want to put the Cox over here, the thickness of the oxide here, because they are constant. It's not changing at all, right? You cannot change the distance between the P1 and P2. It's a standard process, already established. You cannot modify your design to make a different thickness over here. It's the same for the poly and metal. So the metal is going to be here permanently. You cannot make it thicker or small or thinner. Okay, it's the same concept. So that's why we just put the Cox over here and put all the constant over here. So they're not changing. So, but Cox prime is not the cap yet, right? Not the capacitance yet. It's not a capacitance. Because remember, capacitance equals to epsilon times A over D. And this is only the epsilon over, D or T, right? Thickness or distance. But there's no A yet. So that's why Cox equals to Cox prime times what? Just testing, see if you guys are still awake. So Cox equals to Cox prime times what? Okay, here. Okay, here. So capacitance equals to times A, right? So which is the effective A here? The highlighted area. Okay. And for a constant for epsilon r, that's a permittivity of an insulator. In the C5 technology, the insulator is silicon dioxide, ISiO2, and epsilon r of ISiO2 equals 3.97. Here you get the concept. Why do we use epsilon r instead of the real permittivity of the material? So if you look at the numbers, this is really user friendly. You can directly plug in the number over there and calculate it, and it's easier to remember. You don't have to keep using that times 10 to the negative 18th of the time, right? So this is just like the multiples of epsilon O, which is the vacuum permittivity. You know what I mean? So the real permittivity for that material is actually this times epsilon O. We just don't always do that. We just directly use a number here. 3.97 is very easy to remember. Okay, and there are several, because all the materials and metals are very close to each other, so there are a lot of parasitics, capacitance. I'm going to show you. You need to know these things. They're limiting the speed of the circuit. So the capacitance you have is not the only capacitance really exists in the IC chip. If I draw the cross-sectional view for the C5 technology, and the first layer is Fox, and then I got the polys, and then the metals, metal 2, poly 2, poly 1, Okay, so let me know what are these layers. Poly, right? What's in between? Huh? Insulators, right? So silicon dioxide. Is there a cap? Undesired cap. Here as well. Here as well. Even from the metal to the sub. Here as well. So you're wondering, like there are so many caps. You design a cap, but it's not going to be the only cap you have. I mean, it won't be accurate anymore. Yes, it won't be accurate, but the question is, are these caps going to be significant or not, and why? Why? So you just think about that. Do you really um, have a large area of overlapping metals? No. There might be a metal one here, and a metal two here. That's the only cap you have. Okay. What about this one? You usually make these two plates huge compared to all these metal traces. I can give you an example. It's getting so slow today. Look at so here's a little capacitor in a circuit. Where's that? This one, right? 10 picofarads. Only 10 picofarads. It's very small, okay? Very small. Let's look at how big it is in a circuit. So here's how you design a cap. You grab a P2, you grab a P1, add all the connectors, connect the P's to metal ones, and here's the overlapping area. Okay, so the overlapping area, you have to calculate it. It's not the size of the P2 or the P1. It has to be the overlapping area will be the effective area. Okay, keep in mind. And I think the parameter of the capacitance per square is provided. So this is one of the homework assignment. You are going to lay out a cap. And so you can see, so this is one op-amp. It's an operational amplifier. You can see all these transistors are over here. And that's a cap. So the size of the cap is bigger than the amplifier itself. It takes like 70% of the area for the whole design. Why the cap is so big? Why the area is so big? It depends on the Cox prime, right? So the Cox prime is a constant. You cannot change it. So I have to make the area bigger in order to make the 10 pico. So the 10 pico is determined by the design. So in the circuit, I need a 10 picofarads, cannot change it. And now we have to make it happen. So I have to look at the Cox prime of this process. The Cox prime is already a standard number. It's a constant, cannot change. So I have to make the area to a specific area to make it happen, to make the 10 picofarads happen. That's why it's way bigger than the other. We don't want the cap to be that big. I mean, it should be bigger than the traces. It's going to be bigger than the traces anyway, but we don't want the cap to be that big. We want the Cox prime to be a little bit bigger, so it's not taking a lot of space on the chip. The space on the IC chip is very, very expensive. If you can make all the devices smaller, you can integrate more transistors on the device, and you can integrate more functions to the chip, and you can run the chip faster, and you can sell it to more customers. So the area on the IC chip is very expensive. So remember the silicon dies I showed you guys, based on the 500 nanometer. So the ones you are using right now, the 500 nanometer technology. So what's the size of the die? Remember? Dimension of the die, of the silicon die for the chip. It's only 1.5 millimeter by 1.5 millimeter. And that one we can integrate, I think, over 1 million transistors on that chip. But the current, the modern CPUs like the i5, i7, or the Intel CPUs, I think the i5 I'm using here is probably used the 22 nanometer technology. And they can integrate billions of transistors on that single chip area. Okay, if they use the 500 nanometer technology instead of the 22, I mean the laptop cannot be that portable. It's going to be like probably this size. There are so many chips are used, right? Not just the CPU itself. There are so many other ones. If you times 20 for each IC, so the size of the motherboard can be 20 times larger as well. So the size, the area on the chip is very expensive. And so here's the layout, right? And here's the schematic. You couldn't even see the cap on the schematic. Actually, on the layout, the cap takes like 80% of the area. All right. So these are the parasitics. There are many different types of parasitics, and the largest parasitic capacitance in this process is actually the bottom plate to the sub. So that's the largest parasitic capacitance. And the reason is it's very close to the P sub. Remember, the C equals to epsilon A over D. If this is small, it's going to bring the whole cap capacitance up. So it's going to be bigger cap. It's very close. The bottom plate is very close to the P sub. And the P sub, eventually it's being shorted to P plus, and this is grounded. The ground wire is also a metal wire, right? So that's why the capacitance, the parasitic capacitance here is the largest one, and have to consider that in your design. So that's why in the schematic, when you are drawing the poly capacitor, you have to have one of the plate to be different to the other one, because you want to show this one to be the bottom plate. So when you are connecting this to somewhere in the schematic, you want to consider that this pin has a larger parasitic capacitance compared to this pin. Make it different, right? So this indicate the bottom plate. You have like 30 minutes. I think I'm going to give you 25 minutes to the quiz. One more quick introduction to the Miller effect. Since we're done with the C5 layers, you should be ready to do the homework assignments. The next chapter is it's called Models for Digital Design. So after you have learned all the capacitance exists in the C5 technology, so you can use these caps to calculate for the time delays. We can build digital models to analyze time delay when you are communicating with digital signals. So there's a very important effect called the Miller effect. Which is, if you give a voltage rise on one side of the cap, that's how you model the Miller effect, okay? So this is from 0 to VGD. This is from VGD to 0. And here's the cap. It's different from the previous charging and discharging circuits we have used. You usually just have one power source, right? And you charge it up, no problem. You ground the other one, but now it's different. Whenever it's dumping charges into here, this is pulling charges out from the other plate as well at the same time. So actually, the effective charges, the delta Q, the charge change of this cap is actually 2Q compared to the single one, Q here. And this can be confusing, but this is how we model it. So a quick comment on this is, whenever this is dumping charges to here, what's happening on the other plate, just during that time period. So it used to be 0, and when it turns on the switch, start dumping charges to this plate, right? And it's going to form an electric field. Is that correct? So the charges are actually being pushed to the ground. So what charges? Electrons or positive charges? Positive charges. Because these positive charges accumulated over here is going to expel the positive charges on the other plate. Or you can see the electrons are going back. Okay? And Q equals to VC or V over C or C over V. This is confusing, right? You have learned it in circuit 1, right? So which one is correct? Also remember it. I mean, in my circuit 1, I taught it in this way, right? So Q is a queen and has two assistants. One is Charlie, one is Victory. So which is correct? Yeah. Or Q over V is C, Q over C is V, or V times C is Q. If you know this, done. Queen is always on the top. Queen. Okay, so for this one, Q equals to VC, right? Yeah, so for today, we just need to know that there's the effective charges, the charge change to this cap is 2Q, okay? And we're going to cover more about the Miller effect on Friday. Let's do the quiz.